Okay, as you look around the room, I'm seeing a lot of different answers. I'm seeing 1.16, 116 grams per cubic centimeters, 10.5, that's the correct answer. 2.62, I'm seeing a lot of different answers. So I'm just going to go over this from my paper. Because it's a face-centered cube, we have 6 faces with a half of atom, plus 8 corners with an eighth, so we have 4 atoms per cell. And we know that 1 angstrom is 1 times 10 to the negative 10th meters, and I know 4.087 times 10 to the negative 10th meters. There are 1 times 10 to the second centimeters, or 100 centimeters in a meter. So I have 4.087 times 10 to the negative 8th centimeters. If I cube this number, I get a volume of 6.827 times 10 to the negative 23rd centimeters cubed. And I think that's where some of the groups up here ran amok, was in that conversion. Then we know 4 atoms, 108 grams per mole, and 1 mole is Avogadro's number of atoms, so we get 7.17 times 10 to the negative 22nd grams. When I divide my mass by volume, I get 10.5 grams per cubic centimeter. And to me, that seems like a reasonable density for a metal. If you think about water being 1, you'd expect if you dropped some silver metal in there, it would sink right to the bottom. So 10 is a reasonable answer for the density of a metal. Okay, do you have any questions about this? Was the angstroms the thing that really threw you the most? No, for some people it was. I saw a lot of difficulties with the conversions. Okay, so now let's kind of think about how these cells are put together. When we have ionic compounds, the ions that are bigger, which are the anions, form the basic lattice. And when you look back a couple pages at those space-filling models, you saw that there's empty space in there. So what happens is the anions form the lattice. They sit at the lattice points, at the corner, at the base-centered, at the face-centered. And then the smaller cations fill in the spaces. And that's how we can arrange things and come up with that big lattice arrangement. So now we talk about ionic compounds and different kinds of compounds, and even though they are all crystalline materials, they can be distinguished by their crystal type, and the type depends on what is at the lattice points. So if I have an ionic crystal, I have ions at the lattice points. And we recognize ionic crystals because they're hard and brittle, they have really high melting temperatures, and when we dissolve these things in water, or when we heat them up to where they're molten, they will conduct electricity. And that's one way we can identify something as an ionic compound. If we have a molecular crystal, we have either atoms or molecules sitting at the lattice points. And they're just kind of sitting around most times. Because they're just sitting there and they're not particularly attracted to each other, these things are soft materials, they're low melting points, and they are non-conductors, whether they're solid or liquid if they're molten. Typically, they have London forces or dipole forces are the only things attracting them to themselves. There's a special kind of network called a covalent or network crystal, and these also have atoms at the lattice points, but they are different because those atoms are covalently bonded to each other. They're not just sitting there. And because they're covalently bonded, this makes them extremely hard. And when you think of this, what is the hardest thing you can think of? Yeah, besides test 3, right? Diamonds. Diamonds. Those are the classic example of a network or a covalent crystal. And they're extremely hard, extremely high melting points, and they are non-conductors. Then metallic crystals have metal ions at the points, and we see they actually have the positive ions with negative electron clouds. We recognize metals because they are shiny, they're lustrous, they conduct electricity regardless of if they're in the liquid or the solid state, and their melting points and their hardness varies. So what do I expect you to know from this unit? I expect you to be able to understand these different types and recognize them so you can answer questions like these two at the bottom of the page. And you will typically see these sorts of questions in the multiple choice format. Boron nitride melts at 3,000 degrees Celsius under pressure. It's as hard as diamonds. What type is it, class? Covalent. Sulfur is easily crushed. It melts at 113 degrees Celsius. Gives a clear, non-conducting liquid. What type is this? Molecular. So those are the kinds of questions you will see in the multiple choice format on the next test. Okay, this is a good stopping point. We'll go ahead and take our break here.